Hi, and yeah, welcome to our third video in the exploration. This is in a series of explorations. So this is exploration. Wow, the ink is too much. So this is exploration of. Now the ink is too low. Exploration of. So we're exploring what? Aren't we exploring Sylow's theorem? Right. So Sylow has a bunch of theorems apparently, but we're exploring. This is our third exploration of Sylow's theorems. So, well, what is Sylow's theorem? So, the theorem we're looking at now is, look, suppose that G is finite, and we take some subgroup, and the order of G equals to p to the alpha times some m, right? Now here the GCD of p and m is being taken to equal to 1. That is, p and m are being taken to be relatively prime to each other. So what are we saying? Are we saying that, look, if the order of G equals to p to the alpha times m, then we have some subgroup H of G, and this subgroup H of G has the property that the order of H equals to p to the alpha, right? So the idea here is, look, if p is prime and alpha is any integer, I mean, let's say just natural number, then so long as we have a group of order p to the alpha times m, we also guarantee a subgroup of order p to the alpha. Right? So this is a claim. We haven't been able to prove it. And before we're trying to figure out, well, what are the potential strategies for proving such a theorem? That was our key source of confusion. Now, one obvious strategy to try is, well, what if we find some element little g, right? This one strategy you might have seen before. What if we pick some element little g of g and show that if if order of g equals to p to the alpha times m, then this implies that there exists some g in little g in g such that order of g equals to p to the alpha, right? Well, why is this important? Suppose we can find an element of the group of order p to the alpha. Can't we say that the cyclic group generated by the element g? So if you haven't seen cyclic groups, please look up, these are called cyclic groups. So please look them up online, cyclic. Right. Okay. Please look those up online if you don't know what those are. And what's the order of G going to be? Well, isn't the order of G just the same as, no, not the order of G, sorry, the cyclic group generated by G. Can't we just say that that's the same as G to the 0, G to the 1, all the way up till G to the P to the alpha minus 1, right? Well, is this a group? If this group G is a group, aren't we saying that, well, this cyclic group generated by the element G is a subgroup of G? But how many elements are in the cyclic group? Isn't the order of the cyclic group generated by G just the same as p to the alpha? Alright? So then, haven't we just found a subgroup of order p to the alpha in p to the alpha times m in G if we are guaranteed that there exists some element of the group G such that for that element little g order of G equals to p to the alpha? So again, this sounds like a mouthful, but if we can find an element of the group that has order p to the alpha, aren't doesn't that mean necessarily that we have a subgroup of order p to the alpha, right? And we're done, right? So given this information, perhaps that's the first point of attack. Can we find an element of the group that has order p to the alpha, right? So let's suppose that order of G let's suppose that order of G actually still equals to p to the alpha times m. Well, can we find little g? Let's try and find let's find little g in G such that order of little g equals to p to the alpha, right? So what strategies do we have for finding an element of the group whose order is p to the alpha? That's the question. Is there any reason why having a group of order p to the alpha times m will guarantee us an element of order p to the alpha? Again, we have a bunch of tools. For instance, the order of G. Doesn't Lagrange's theorem guarantee us? Again, if you're confused about this, please check out Lagrange's theorem. Lagrange, this is the word. So just check out exploration of Lagrange's theorem. Right. Lagrange's theorem, and we talked about, we did an exploration of Lagrange's theorem, and one of the things that the exploration seemed to conclude was that if you have a finite group, then the order of every element of the group must divide the order of the group. In this case, doesn't that mean that order of little g must divide p to the alpha times m? So maybe saying that the order of every element must divide p to the alpha times m may help us to find an element of order p to the alpha. But how is that helpful is the question. Well, how does the fact that the order of every element divides the order of the group lead us to conclude that p to the alpha time, that we must have an element of order p to the alpha? Again, it doesn't seem to be clear. I mean, the only thing we seem to be able to gain from here is that the order of little g equals to p to the 0, or p to the 1, or p to the 2, or dot dot dot, all the way up till what, p to the alpha, or, well, mixtures of powers, right? So couldn't we have, like, let's say p to the 2 times m, or maybe p to the j times some factor of m, let's say some k, where k divides m. So one strategy we may think about is, well, why don't we find all the possible divisors of p to the alpha times m and show that, well, all of them don't work, that the only divisor that works is p to the alpha, right? That none of them work except for p to the alpha. But our only issue here is that, one, we don't know how many divisors there are, or at least, even if we're able to know how many divisors there are, do we have a way of eliminating? Do we have a way of eliminating all the other options so that we are left only with p to the alpha, right, as the possible order for some element g, right? So again, this doesn't seem clear. Perhaps it will come together in this solution, but we're not sure how finding an element, how we're going to find an element of order p to the alpha, at least not by elimination. So this begs the question, is there some other way we can guarantee that if the order of the group equals to p to the alpha times m, that we are guaranteed an element of order p to the alpha, right? Is there any way to guarantee that? You know, hopefully not just think about elimination, because elimination, at least at the moment, doesn't seem to be helping us. It may help us in the future. We never know. You know, it's a mystery how these solutions come together in the end. But so we're just trying to learn as much as we can about our problem here. So one approach might be, suppose we showed that order of g, that there's an element such that its order of g has no factors in common with m. That is, if you look at the prime factorization of order of G and the prime factorization of M, well, there's nothing in common, right? Then wouldn't that mean that we have an element G such that order of G equals to, well, since it has no factors in common with M, can it possibly divide M? Okay, if it can't divide M, can we at least say that we found an element whose order, if it can't divide M, but its order must divide the group, does it mean that that element divides P to the alpha? Okay, well, if you have an element that divides P to the alpha, is there any way for us to guarantee that we're going to have a subgroup, that we're going to have a subgroup of order P to the alpha, right? So isn't it possible that the order of G may be equals to P to the I, where I is less than alpha, right? But there is no, wait, isn't that possible? In which case, sure, we found a subgroup. Haven't we found a subgroup G to the 0, G to the 1, all the way till G to the P to the I minus 1, the cyclic subgroup here. But unfortunately, this cyclic subgroup has cardinality less than P to the alpha. It has cardinality P to the I, which seems to be less than P to the alpha. And so we're not sure again if this strategy is going to help us. Unless we show that, perhaps if we can show that we have an element which has no factors in common, that is GCD of, so maybe if we can find the following. If we can show that the GCD of the order of G and M equals to 1, that is if order of G and M have no factors in common, and we're also able to show that if we're able to find some G such that its order with the order of G with M the order of G and M have no factors in common, and also we have the fact that order of G does not equal to P to the I, where I is less than alpha, right? If we could do that, then wouldn't we also be done, right? Because if we show that no smaller power works, right? If we show that no smaller power than alpha works, and that the order of G has to be of the form P to the theta for some theta, doesn't that mean that if no power smaller than P to the I works, but order of G definitely divides, and order of G definitely, if we're saying that order of G definitely divides P to the alpha by Lagrange's theorem, doesn't that necessarily mean that order of G has to be P to the alpha? So this seems to be like a roundabout way of maybe showing this, but could we show the specific steps? That suppose we know that a group has order P to the alpha times M. Can we guarantee that there's an element whose order is relatively prime to M? And if we can guarantee this, can we guarantee that for this element little g, its order can never be less than P to the alpha? Right? If we can do that, we're probably done as well, right? So let's see, maybe let's try the first step. Suppose order of G equals to P to the alpha times M, right? Does there exist little g in G such that GCD of little g such that GCD of little g with M always gives us 1. That is, does there exist some element whose order is relatively prime to M? Are we guaranteed that this is always true, right? This is a question. At least off the bat, it's not clear. off the bat it's not clear that we must have such order of G. Maybe we can work by contradiction. Suppose there does not exist little g in G such that suppose there does not exist little g in G such that GCD of order of G right? Suppose this little g doesn't exist such that GCD of order of G with M equals to 1, right? So suppose such a little g does not exist, right? What does that mean? Doesn't that mean that for all elements of the group G, doesn't this mean that GCD of order of G right? GCD of order of G and M, aren't we saying that that has to equal to cannot equal to 1? That is, aren't we saying that for every element G, it's the order of every element has to have something in common with M. That is, order of G and order of M are not order of G and M are not have some prime factors in common, right? So again, it's still unclear here. Um, it's still unclear here. If we could obtain a contradiction here, then wouldn't we be saying that there has to exist at least one G that such that its order is relatively prime to M? And if we have that, right, can't we at least say that, well, whatever the order of G is, the order of G has to divide P to the alpha? And then from there, maybe try to establish that the order of G cannot be less than P to the alpha either. So let's see. Or at least in this, or at least find some element, let's say Gi, such that order of Gi cannot be less than P to the alpha, and maybe Gi is also such that order of Gi divides P to the alpha. Okay, so this again is a mouthful, but are we guaranteed of this? But first, before we even get here, suppose we know that there is no element little g such that the order of little g and M have any prime factors in common. Why does this necessarily lead us to conclude? How does this lead to a contradiction? If order of G and M don't have any prime factors in common, so what? Well, what does that mean? Sorry, if they always have a factor in common. If order of G and M always have a factor in common, I've been saying it wrong for a while. If if for all G and G, order of G always has a factor in common with M, what are we saying? Okay, can we at least conclude from there that, well, if we look at the possible, if we pick some G and look at the possible orders of G, aren't we saying that all of them must be of the form P to the I times some, let's say, L, where L is some divisor of M, right? Would you buy this? Because if order of G and M always have a factor in common, right? Well, actually, couldn't it be that order of G equals to M? Okay, maybe that's another possibility. So, well, actually, that would still be fine, right? That would still be something of the form P to the I times L, where L is a divisor of M, and we're saying here we're trying to emphasize that L does not equal to 1, right? So, because if L were equal to 1, then we're just saying order of G equals to P to the I, something which is stuff we've already been looking for. So, Right. So does this follow, by the way, that if order of G and M have something in common, then it means that order of G is of the form P to the I times some L divisor of M, and this divisor of L is not just 1. It could be, it's just some other divisor, non-1 divisor of L. So, okay, so from here, if the order of every element is of the form P to the I times L, why is that, why is this useful information? What are we going to do with this? Can this lead us to some contradiction? We notice that though, like, if order of G equals to P to the I times L, aren't we saying that the group G to the 0, the cyclic group generated by G, right? Right. Again, if you're confused about cyclic groups, please check out the videos on please maybe go online on YouTube or something and learn about what cyclic groups are. But if you look at the cyclic group generated by G, we're saying that its order equals to P to the I. It's the order of that cyclic group. If order of G equals P to the I times L, doesn't that mean that the order of the cyclic group generated by G is also P times I, P to the I times L? Okay. Let's write it like that. L. Okay. It's supposed to be L. Alright. Alright, let's maybe write a little more clearly here. Right. Okay, P to the I times L. Well, aren't we saying that then our cyclic group, let's give it a name, generated by G? Well, we could just, let's call it R or something. Okay, so R is our cyclic group generated by G. Aren't we saying that isn't this R also of the form P to the alpha times some number? And isn't, if L is a divisor of M and GCD of P and M, right? So this symbol means GCD of P and M. If we said GCD of P and M was equal to 1, right, doesn't that mean also that GCD of P and any divisor L of M, right, any just non-1 divisor of, right, any non-1 divisor of M is also going to equal to 1. Right? So could we perhaps get a reduction here where we keep reducing powers? So before we started with something of the form P to the alpha times M, we said that, well, if every divisor of P to the alpha times, if every element of little g has order, is such that order of G is of the, okay, so if for all little g and G, if we found that order of G always has something in common with M, that is, order of G and M are never relatively prime, well, right, if that's true for the group order of G equals P to the alpha times M, right, then aren't we saying from there that, well, at least that the cyclic, that, okay, aren't we saying there that every element has order P to the I times L? If every element has order P to the I times L, well, isn't this in the same form for Sylow's theorem? And so, well, here, perhaps if we can guarantee here also that, well, right, actually this makes sense because, okay, over here, right, in the for the group R, for the subgroup R, right, for R subgroup of G now, right, we've got a subgroup which is a cyclic group generated by G, right? Is it possible for, let's say, for us to find some little r element of R such that um, order of R, uh, well, is not of the form P to the J times L, right, times, let's say now, T, where, well, J is some power, right? We obviously think of a power less than P to the I, or at most P to the I, right? Because R is being taken as an element of R. Little r is being taken as an element of big R. and T is being taken to be a divisor of L, that's not 1, right? T not equal to 1, non-1 divisor of L. Well, suppose that we found suppose that actually T were equal to 1, right? So we found an element little r in R such that order of R just equals to P to the J. Okay? Well, if this R is an element of R, if little r is an element of big R, and big R is a subgroup of G, isn't R an element of G as well? Right. If R is an element of G, and we found an element R whose order is just P to the J, right? Weren't we then mistaken in assuming that there is no element in the group G such that the order of that element is P to the J, right? Because we said before that, right, part of our assumption here was like, look, for every element, the order of the element must have something in common with M, some non-one factor in common with M. The GCD of the element, of the order of the element with M cannot be 1. But now haven't we just found an element in the group, right, whose order is P to the J, which means that, doesn't this mean that the GCD, right, that the GCD of order of R with M, right, doesn't this mean that the order of the GCD of the order of R with sorry, with M has to equal to 1, because look, M has nothing in common with P, right? Because GCD of M and P is 1, and order of R is just a powers of P. So how can P to the J have anything in common with M, right? Right, so obviously we're saying here if we can find some R not equal to the identity, some non-identity element R in R, for which order of R equals to P to the J times T. So, right, so we're really like deeply engrossed in the proof. A lot is happening here. So let's see, let's make sure we're clear in what we're doing so far. Right, if there is no element, if order of G and M are never relatively prime, then every element is of the form P to the I times L. This gives us the subgroup generated by little g, which has order P to the I times L. Fine. And we're saying that, look, there actually can't be an element of R that's just of the form P to the J, whose order is just P to the J, because if that were true, then order of R would be relatively prime to L, right? And if order of prime is, if GCD of the order of R and L is 1, right? Doesn't that mean that, and we might not even need to go there, if just, right, if GCD of R and L is 1, doesn't that mean that order of R and L have nothing in common, right? Which doesn't that mean that order of R necessarily has to be P to the J? But if order of R is P to the J, doesn't that tell us that, look, we've actually found some element in the group whose order is P to the J and has nothing to do with M, right? So here we seem to be saying that, look, whatever, every element, and we're also saying that for this P to the IL, that is, now for R equals to the group generated by G, which equals to P to the, okay, so, okay, so, let's see, maybe we have a promising strategy here. So, we start with order of G equals to P to the alpha times M. We say that, look, this is telling us that this right here, saying that order of G equals P to the alpha times M, we're assuming that, well, that's telling us that there is no subgroup. We're supposing that there is no subgroup sorry, there is no element whose order has anything in common with M. So for all G, we're assuming that for all G, order of G, right, the GCD of the order of G and P, sorry, and M, right? So maybe we can't prove everything. Maybe we'll be able to prove a special case. So here's what we're supposing. The GCD of the order of G and M equals to 1, right? This is what we're assuming so far. Order of G and M are relatively prime for all G, right? Relatively prime can never are not relatively prime, right? So they always have some factor in common that's not 1. So, and we're saying that, look, isn't this telling us then that the cyclic group generated by little g, right? That is, isn't that telling us then that, okay, so let's sanitize this whole thing. So, and we're being told here that, look, if that's true, then for all little g, right, does that mean that for all little g and g, okay, we run out of time, so then that means that for all little g and g, and we're saying that the order of g has to be of the form p to the I, right, times m, right? If, sorry, no, not p to the I times m, but p to the I times some l, right? So some l, and the idea here is, once again, as we're saying before, look, if all elements have something in common with m, then that means that if we take order of g, well, some of its factors are divisors of m. So let's call the factors of g, of order of g that divide m, l, and then maybe we'll have the prime p raised to some power. Okay, right? And here obviously I is at most alpha, isn't it? Right? Because the order of g has to be something that's at order of g has to divide p to the alpha times m. So can the power of alpha ever exceed alpha? Right? Can the power of p to the alpha, can the power of p ever exceed alpha? Right? So from here we're concluding that, look, this tells us the following, that this subgroup here, which we're calling R, big R, this subgroup generated by the element G actually has order of R is actually equal to the cyclic group generated by G is actually equal to p to the I times L. Right? Okay. And the other thing we're noticing here is that, look, actually one thing here that's happening is that here we're saying that L divides M, right? L is the divisor of M, and L can't just be 1, right? Because order of G and M is not 1. They have more in common than just 1. Okay, so L can't equal to 1, right? And now we're saying, look, if we actually look at this subgroup R of G, right? One thing we know that it has to be the case as well for this subgroup R of G. It has to be the case that for all little r in R, right? Is it the case that for all little r in R, it must be true that order of R equals to p to the j times some k, where k divides L, right? And k is not just the identity element, right? So, well, why is this true, right? Suppose not, right? So let's suppose that there actually exists some R. Let's suppose there exists some R in R such that order of R is of the form p to the j, but the k that we have here is 1, right? It's just 1. Okay, it's just p to the j times 1. Does that mean that order of R equals to p to the j? But if order of R equals to p to the j, right, and we're saying, haven't we found some R, because if R is an element of, little r is an element of big R, why did we write it like this? It's just normal R, it's not the real numbers, right? So, not the real numbers. So, if little r is an element of big R, and R is a subgroup, big R is a subgroup of G, doesn't that mean that little r is an element of G? So haven't we just found an element of G, haven't we just found some little g, namely r? Haven't we just found some little g in G such that order of G equals to p to the, in this case, p to the j times, and it has nothing in common. That is, haven't we just found some little g such that the GCD of the order of G, the GCD of the order of G with m, right, actually equals to actually equals to 1, right? And isn't that a contradiction? Because we assume that no element of R can ever have a GCD that's equal to 1. For every element of the group G, its order cannot be relatively prime to M, right? Isn't that what we supposed here, that for all G, order of G, GCD of order of G and M cannot equal to 1, right? So again, does there appear to be a problem with this argument? No. So what is this telling us? This is telling us that, look, if we now look at our new group R that we formed, our group R that's a cyclic group generated by G, and that is of the form and has order, is such that order of R equals to P to the I times L. L is a divisor, where L is a divisor of M. One thing we're able to find from this entire exploration is that, look, for all R in R, for every element of R, don't we now know that at least order of R, right, has to be of the form P to the J times some K, where K divides L, and K does not equal to 1. Okay? If that's true, right, if that's true, doesn't this mean that we can now think of, well, the subgroup generated by little r, right? And isn't it also true that for the subgroup, notice that the j's are going down in power, so the little j's are going down in power, j is reducing, and also we started with m, and then we picked out the divisor L, right? And we picked out a divisor K. So doesn't that mean that also these entries, doesn't that mean that P to the M, right? P to the M times, P to the alpha times M, right, is strictly bigger, right? Is strictly bigger than P to the I times L, right? Which is strictly bigger than, well, actually, it does have to be, it could be less than or equal to, couldn't it? Okay. And then this was just P to the J times K, right? So maybe if we get rid of this strictly, if somehow we can get rid of the strictly bigger thing, sorry, the less or equal to part, so that P to the alpha times M is strictly bigger than P to the I times L, which is strictly bigger than P to the J times L times K, maybe we can do the reduction and end up with, let's say, just something, guarantee that there must be some element little g such that the order of little g equals to just P to some element, let's say C, P to some C. And this will lead to a contradiction, which maybe would be able to tell us that there must exist some element in the group little g such that the element little g is such that the order of g equals to just the GCD, at least the GCD of the order of G, and maybe we'll come to the conclusion that since if we gain a contradiction from this reduction from P to the alpha to the M to P to the alpha times M to P to the J times K, maybe this reduction could lead us to a contradiction, right? To the fact that the GCD of order of G and M always can never equal to 1, right? Because if we find any element of order P to the C, right, haven't we just contradicted the fact that, right, that the GCD of the order of G and M cannot equal to 1, right? So if that's the case, then doesn't that mean that we are guaranteed at least one element such that the order of that element, right? GCD of the order of that element and M actually equals to 1, right? What does that mean? Doesn't that mean that we found an element such that the order of G is only p to the I, some prime power, p to the, let's say p to the I, right? Some prime power. And if we are guaranteed such an element, perhaps maybe we can prove that I can never be less than alpha, right? Or that I has to equal to alpha, right? Maybe that's the strategy we're going to use. So this is a little convoluted. Please do think about it. And it's all with the same goal. We want to conclude the following, that if the order of G equals to p to the alpha times m, where p and m are relatively prime, then we are guaranteed a subgroup H of G such that, this is G, such that the order of H actually equals to p to the alpha, right? So we've identified one strategy, and the cool thing is the most advisable thing is let's try this strategy out and let's try to make it work. If it doesn't work, we can confidently rule it out and move to a different approach, right? But thank you very much for watching this video, and have a relentless week. Bye.